Oops. Thanks, Nikhil. This is joint work with Siddhant Mohanty, who's right here. He was an undergraduate at Carnegie Mellon. We were working on this together, but now he's a grad student at Berkeley, so you can see him around and high-five him in halls. OK, so we proved some things about a variety of infinite graphs. And I'll say what infinite graphs in particular later, but for now I'll just give you some examples to which our results are going to apply. So here's one. Of course, I can only show you a finite picture of them, but this is the infinite graph where you take a triangle, and on each vertex you attach two edges, and then at every vertex there's attached a triangle and two edges. And for the sophisticates, this is the free product of the triangle and two edges. Here's another one. This is just the infinite three-regular tree, which I'll call T sub 3 in this talk. That's an important example. And again, for sophisticated people, this is the free product of three edge graphs. That's T4, the infinite four-regular tree. This is a non-regular graph, but in a very simple way. This is the infinite biregular 3, 4 tree. I just put this up here to say that some of the graphs will not be regular. This is another graph that's even simpler than earlier ones, but it's the product of a free product of a triangle and an edge. And I only put this one up so I can say this fancy name. Apparently it's the Cayley graph of the modular group. There's another graph. This is the free product of three 4 cycles, two 4 cycles. And let me pause on this one for a second. This is another infinite graph that kind of looks like you put down C4 with K4 minus an edge, and then another copy of K4 minus an edge, etc., in such a way that the diagonals don't touch. This is not the free product of any particular graph. So in fact, I wrote this tiny thing down here. So one thing that we do in this paper is introduce a new kind of graph product that takes some finite graphs on the same vertex sets. And when you graph product them, you get an infinite graph. So I'll explain more about that later, but this infinite graph we call this the additive product. It's the additive product of these two little graphs. Okay, and it depends on the labeling, the vertex labeling of the graph, so these are not the same graph. And I don't know, here's one more example. Yeah?
If the two graphs had been the same, that would have been a free product? Or?
No, it's not clear, because free product of graphs actually involves them having a root. There's only free product of rooted graphs. So many of the nicest examples involve little graphs that are vertex transitive, and then it doesn't really matter what the root is. Yeah. So here's one more random example. It's again going to be one of these additive products that we invent, and I put it up here because these graphs don't even have to be connected. OK, anyway, so there's going to be some wide family of infinite graphs involved, and we're going to prove some things about their spectrum and eigenvalues and stuff like that. OK, so the story is going to involve fixing one particular infinite graph x, I don't know, maybe this one. And then what we're going to do is look at all the graphs which are so-called finite quotients of these graphs. All the finite graphs, here's the definition, but basically a finite graph G. In this talk, G will be a finite graph, and X will be one of these nice big infinite graphs. G is the quotient of X if it kind of locally resembles X. So more properly, there should be some surjection from the infinite graph to the finite graph that locally looks like a bijection. I'll give you some examples. But basically, we're going to be looking at, once you fix the big infinite graph X, finite graphs G that locally resemble it. OK, so this is the first infinite graph we looked at. And here's an example. I mean, it's not easy to tell right away, but here's an example of a finite graph G, which is covered by this infinite graph. And in fact, the set of finite graphs covered by this infinite graph are all those 4 regular graphs where every vertex participates in a triangle. It's not too hard to prove. OK, so this graph sort of locally resembles this graph. Now, these things are not necessarily unique. So this graph is also covered by, or a quotient of, the infinite 4 regular tree. Okay, so one graph can be covered by different infinite graphs. And in fact, the set of all finite quotients of the infinite 4 regular tree are just the 4 regular graphs. Okay, so this is still a 4 regular graph, but it had this additional property, actually, that every vertex participated in a cycle, a 3 cycle, which meant it was also covered by the previous guy. OK. Great. so fixing an infinite graph X, we're going to be studying all the finite graphs that are quotients of it. And it's a simple fact that all of these graphs have the same largest eigenvalue. So I'm going to use this notation, lambda 1 through lambda n, for the eigenvalues of the adjacency matrix of the graph G, ordered from largest to smallest. Okay, so all the finite quotients of an infinite graph have the same largest eigenvalue. And in particular, if the infinite graph is delta regular, then so are all the finite graphs. And this common eigenvalue is the trivial eigenvalue, namely delta. Okay, so in light of this, we're going to be talking about expanders and Ramanujan graphs and so forth. We're going to be interested in how small the second largest eigenvalue of these finite graphs G can be among all the graphs covered by X, all the graphs that locally resemble X. And one reason for this is that this gap between the largest eigenvalue and the second largest eigenvalue is some kind of spectral measure of how good an expander this small graph G is. If you think about expanders, and you also might worry about how large the negative smallest eigenvalue of G is. But we're not going to worry about this in this talk. So we're only going to be worried about how far away lambda 2 is from lambda 1, or how small the second largest eigenvalue can be. Okay, so we're again fixing X. We're interested in statements that look like this. For given X, there are infinitely many finite graphs that are covered by X, whose second largest eigenvalue is smaller than some number rho star. So we want to get a lot of finite graphs that have small second eigenvalue. And the first thing we should ask ourselves is, what's the best possible rho star, the smallest possible rho star we could ever put here? And there's a barrier to how small this can be that comes from X. So you may have seen this before in the context of just delta regular graphs. This is the Mellon-Bapana theorem. And there's generalizations of it by Greenberg and Grishorchuk and Zook and others. And what they say is you could never put, for a rho star here, any number which is smaller than the spectral radius of X. That is to say, the largest eigenvalue and magnitude of the infinite, parent graph X.
You're using L2 on the universal Hilbert.
Pardon me?
You're using the spectrum on the Hilbert space of square integrable. It's very important.
Yes, that's right.
You could take bounded functions and then it would not be true.
Yes. Good. Okay, so the classic Mellon-Bapana theorem case is when the infinite graph is just a delta regular tree. And so the finite quotients of it that we're studying, that just means all the delta regular graphs. And it's a well-known fact that the spectral radius of this infinite delta regular tree is this magic number, 2 square root delta minus 1. And therefore, the Mellon-Bapana theorem in this case says that whenever you have a finite delta regular graph with n vertices, its second largest eigenvalue has to be at least basically 2 root delta minus 1, minus little of 1. Actually, you can say stronger things than this is commonly attributed to Serre, the stronger result, that in fact, for any fixed k, even the kth largest eigenvalue has to be at least this magic number, 2 root delta minus 1, minus little of 1. And even that linear fraction of the eigenvalues have to be bigger than this spectral radius of the infinite graph. And this has a generalization to the case where this infinite graph is not just a regular tree, and it's not just a tree at all, in fact. So in fact, Grigorchuk and Juk showed that for any infinite graph X, if you look at all the finite graphs covered by it, their second largest eigenvalue always has to be basically at least the spectral radius of X. Okay, and in fact, this stronger generalization about a linear fraction of the eigenvalues is also true. Good. So that kind of tells us, if we're interested in studying finite covers of X, what the smallest thing we could sort of shoot for potentially is here for the second largest eigenvalue. Okay, so let's put yourself back in the mind of just X being the infinite delta regular tree, and therefore the graphs we're interested in being the delta regular graphs. So we have this Mellon-Bapana theorem. And then the traditional definition of a delta regular graph being Ramanujan is just to say that this bound is met. In other words, that the second largest eigenvalue of G is at most this magic number, the spectral radius of the infinite delta regular tree. And these are really cool graphs, the optimal spectral expanders among, in this case, delta regular graphs. Okay, but part of our motivation in this paper was to study the same question, but not for graphs that locally resemble regular trees, that may locally resemble some other infinite-looking graph, infinite graph. Great. So as to whether there are any such Ramanujan graphs. Oh, sorry, I didn't say this here. So here's the general definition that we're going to work with. So it's a general notion of being Ramanujan, and it's not a property of the finite graph. It's sort of a property in some sense of the fixed infinite graph. So you fix an infinite graph x, and then you say that a finite graph covered by that x is X-Ramanujan if its second largest eigenvalue is bounded by the spectral radius of x. I think this definition is due to Grigorchuk and Zook. Okay, so as for the existence question, in the case where you have the infinite delta regular tree, it's a result of Lubowski, Phillips, Sarnak, and Margulis that these guys exist whenever delta minus 1 is a prime. We constructed infinitely many of them. And then this was upgraded to prime power by Morgenstern. And then this was just upgraded to any value of delta by Marcus Spielman and Srivastava. And they did it via the interlacing polynomials method that we heard about in Nima's talk. So great. This existence question solved when x is the infinite delta regular tree. In fact, they prove more in their interlacing polynomials 4. They basically show the same result, more or less, for x being any infinite tree. Any infinite tree which covers at least one graph, which is to say any universal cover tree x. So if you look at another paper, they show that whenever x is some infinite tree, and it covers some finite graph g0, they show that there are infinitely many lifts g of g0. So I'll get into talking about lifts later, but this is a way of constructing larger finite graphs from smaller finite graphs. So in particular, all these lifts g of g0 will also be covered by x, such that basically all the eigenvalues of the resulting graph, except for a constant number, are bounded by the spectral radius of x. So it's a fact that when you take a base graph g0 and form a lift of it, the eigenvalues of the lifted graph include all the eigenvalues of the base graph, including the trivial one, the largest one. And so they showed you can always find lifts, infinitely many lifts, where all the newly created eigenvalues are upper bounded by this target, the spectral radius of the infinite tree x. Okay? So in particular, if the base graph itself was Ramanujan, if you find like one Ramanujan base graph whose all but top eigenvalue are bounded by the spectral radius, then so will be all the lifts. And this proved conjectures of Bielu-Linial and P. Clark. So as I said, this shows that if you just have a single X-Ramanujan graph g0, in the case where x is a tree, then there are infinitely many X-Ramanujan graphs. There are infinitely many Ramanujan graphs for this infinite tree. And even if you can't find this base Ramanujan graph, it's still kind of cool. I mean, it's still kind of okay. You get something that P. Clark calls a quasi-Ramanujan graph. Just whatever like annoying eigenvalues of the base graph were bigger than the spectral radius of x stick around, but all the other ones will be bounded by the spectral radius of x. Okay, so there'll be, this just notates that like at most k0 eigenvalues are above the bound that you care about. And this is natural given that these like stronger Alon-Bapana theorems that say that even a linear fraction of the spectrum has to be basically at least the spectral radius of x. Okay, so this is all for trees, but as I mentioned before, we kind of want to do the same thing. Our motivation was to do the same thing, but for infinite graphs that are not trees. In other words, for graphs that have like some short cycles in them. Graphs that resemble some of these infinite graphs, the pictures of which I was showing you at the beginning. And our main theorem is that this same theorem, exact same theorem, holds for any infinite graph x, which is an additive product graph. And I'll explain what that is later. But in particular, that includes all universal cover trees. And it includes all graphs which are free products of vertex transitive graphs, which is kind of a lot of the nice looking infinite graphs. And it includes some other graphs. Questions? Yeah.
Group which is a surface group. I think maybe I've asked this before. So it's the fundamental group of a Riemann surface of genus G. So it's got one relation, A1, B1, A1 inverse, B1 inverse, that's A2, B2, B2, A2 inverse, B2, all equals 1. So it's got one relation, it's not a free product of cyclic groups. So, and nobody knows how to compute the spectrum of that separately.
Yeah.
You can handle anyway?
No. So two things I'll say. One is that this raises an interesting point, which is that we're going to prove this theorem without necessarily computing the spectral radius of X. Yeah. So we're actually going to prove this even without like knowing what is the spectral radius of X. That's one thing I'll say. And I don't know all the details of the example you asked, but like an example graph X that we care about and don't know what to do with would be like the infinite grid graph, like Z2. That's not an additive product graph, but we would be interested in that. Okay, so we want to follow the same method of producing large finite graphs that are X-Ramanujan graphs. But there's a problem. The only way we know how to do this in the usual case, the normal case, produces graphs that locally resemble trees. But we don't want graphs that locally resemble trees. So we need to invent a new kind of lift, which I'll tell you about, and we call it additive lifts. So let me define what is the additive lifts. And they're going to be random additive lifts. So I'll sort of define random additive lifts all in one shot. So the funny thing is we're not going to apply this just to one base graph. We're going to talk about additively lifting a collection of finite graphs. And all these graphs are going to have the same vertex set. And we like to call these finite graphs atoms. And we also like to color them. So let A1 through AC be graphs on the same vertex set. And we're going to talk about additively lifting this list of C graphs. Here's going to be my running example. I have 4 atoms in this case, and they're all on the same 3 vertices, U, V, W. A1 is a triangle, and the other 3 are just single edges. But they remember, I don't delete this isolated vertex. Okay? So I'm going to talk about making additive lifts of this collection of 4 graphs. But before I get to additive lifts, let me talk about 2 simpler operations on collections of graphs. The first operation is very simple. It's just summing. Sometimes I'm going to identify graphs with their adjacency matrix. And summing just means put the graphs on top of each other, or sum the adjacency matrices. So in this particular running example, when I sum these 4 graphs, I get this multigraph. We're going to be fine with multigraphs in this talk. So we get the 2 copies of the triangle. Okay, so that's summing, an operation on collections of graphs, atoms on the same vertex set. Okay, the next operation I need to tell you about, and by the way, the additive lifts are going to be a combination of summing and this operation. The second operation is called making a balanced lift of a single atom. Okay, so it's going to resemble a normal lift of atoms, but it's going to be a special case of this. But in the end, we'll come to a generalization. So let me tell you what it means, a balanced lift of a single atom like this triangle graph. So in a balanced R-fold lift, it's going to sort of resemble the normal lifts, which perhaps you've seen before of a graph. So step 1 is you make R copies of the vertex set. So in my example here, R is going to be 4. I'm going to make a 4-fold balanced lift of this triangle. And then I'm going to put some edges in here. So the first thing I'm going to do is I'm going to put a random permutation on the symmetric group of order 4, or R, on each vertex. This is different from the usual lifts where you put random permutations on the edges. I'm going to put a random permutation on each vertex. Okay, so here's an example. But now I'm going to get permutations on the edges by taking the quotients. Okay, so for every edge in the graph, I'm going to take the quotient between the permutation on the vertices, which I've illustrated here. You can trust me on that. And now I have a permutation on each edge. And now I'm going to do like the usual lift thing of I'm going to put a matching between, let's say for every pair of vertices u and v in the original graph, I'm going to put a matching between the u vertices and the v vertices here according to this permutation that's on the edge. Now, these are usual lifts of the base graph. Perhaps it'll look like this here. But they're not as general as possible. There's something special about them. In particular, you see, because of this permutation on vertices thing, these edge permutations have the property that whenever you walk around a cycle, you get back to the identity permutation, because all the quotients like cancel out. Okay? This graph is a bit funny because the whole graph is one cycle. But in general, if this atom graph has some cycles in it, then these edge permutations will have the property, this is the balancedness property, that when you go around the cycle and multiply the edge permutations, you get back to the identity permutation, which means that the same cycles occur back in this big graph. And therefore, for example, this big graph will have short cycles all the time if this base graph has cycles, which is something that doesn't more or less happen in a random usual lift. In fact, it's more than that. It's not hard to show that, I'm just going to say here that in the usual lifts, the usual random lifts, you just put independent random permutations on the edges and then do this construction. So this is a special case of the usual lifts. And it's in fact not hard to show that when you do this operation, you just get R disjoint copies of the base graph. So in this picture, which I just widened a little bit here, it should be the union of 4 triangles, which it is. So there's 1, 2, 3, 4. This edge is just going behind this U3. It's not connecting to it. Yeah, so it's a bit of a structured way to make R disjoint copies of the base graph. Okay, so it may look like I'm defining something less general than the normal random lifts. But actually, when I put it together with the summing operation, we'll see in a second that it can be more general. Any questions? OK. So, right. So I defined summing base graphs, and I defined balanced lifts. And now, to make a random additive lift, you just do both. So you do a random balanced lift of each atom, and then you just put the results on top of each other. So here's an example. This is a 4-fold lift I created of each of the 4 base graphs. It's a little hard to see. Then you put them on top of each other, and then this is the lifted graph. There aren't inherently colors, or the colors are just illustrative. It's just this ugly graph. Here's another example. This is a 10-fold lift of the original graph. Remember, the original 4 atoms were like 1 triangle and then 3 edges. And you see that this 10-fold lift, yeah, you see like the disjoint yellow triangles in it, and at each vertex it's connected also to 2 edges.
So,
yeah.
Do you pick the same random permutation for vertices for each of these atoms?
No, independent ones for the different atoms. Good. Let me make actually just one small remark on these balanced lifts. Whenever you have a single edge, or in fact more generally a forest, the balanced lifts are the same as the usual lifts. Or a balanced random lift is the same as the usual random lift because there are no cycles. OK, so although, let me tell you now actually how these random additive lifts, in fact, generalize the usual random lifts. And it's going to be by an operation that I'll say a few times. Let's say you just have like one base graph. You're just in the world of one graph. The thing I always want you to do in this talk is imagine like going to this world of like atoms by exploding it into what I'll call its edge atoms. In other words, just writing it as a sum, kind of like Nima did in his talk with the little edge Laplacians, a sum of one edge graphs. Okay, so I'll always, whenever I have like one graph, I'll like convert it to the sum of one edge graphs. Oh, I think I have to say this in words. So imagine what happens if we do an additive lift of these 4 atoms now. Well, first we do like a random balanced lift of each of these single edge graphs. But as I said before, I mean, OK, you take the quotient of 2 random permutations, you just get a random permutation. So these will just turn into like random matchings between the appropriate pairs of vertices. And then you'll add them back up. And this is exactly what you do in the usual random lifts, if you're familiar with the usual random lifts. OK, so if you just start with any, what I'm saying is if you start with any graph here, explode it out to its edge atoms, and do this additive, random additive lift to it, the resulting graph is just a random usual lift of the original base graph. Okay, so again, here's my running example of 4 atoms. And if I do a 4-fold additive lift, it might look like this. And if I did a 10-fold additive lift, it might look like this. And what if I do like an 1,000,000-fold additive lift? What will the graph look like? Well, in fact, I want to ask, as r goes to infinity, what infinite graph does an r-fold additive lift locally resemble? You can imagine it, right? It's basically going to be like, in this particular case, like the infinite graph, where let's say you plunk down a yellow triangle, and then if this is vertex u, then you would attach like a pink edge and a blue edge. And then at those vertices, you would attach one copy of each of the other graphs and so forth. I mean, it's kind of like, when you do the balanced lift, it's kind of imagine that there are like no like coincidences about like when you start walking for a bit that you come back to a layer you've seen, except for those necessary ones based on the fact that like, well, there's going to be copies of the cycles of the base graph in your graph. So I actually want to say just the answer is what we're going to define the additive product to be. So that infinite graph that maybe you can imagine is what I'll take as the definition of this additive product of these 4 atoms. So of course in the paper we write a proper definition of what is the additive lift of some atoms, and it resembles the definition of the universal cover tree, but it's a bit more annoying. But you can get the correct idea just by saying, oh, it's that infinite graph that these things resemble when you take larger and larger lifts. So I'll draw you some pictures here to illustrate it. So the additive product of these 4 atoms is this infinite graph. Again, the colors are just for illustration, but you plunk down a copy of one of the graphs. It doesn't matter which one you start with, and then put copies of all the other graphs on the vertices that you haven't touched, and then on the vertices you still haven't touched, you put copies of all the base graphs that touch that vertex, sort of, and so forth. Okay, so here's another example. If I just have 2 atoms that look like this, then their additive product is the infinite graph that starts to look like this. Okay, so again, you put down a copy of this graph, and then at each vertex attach this graph appropriately with the labels of the vertices, and so forth. And also now let's put yourself in mind of the case where you're just given one graph. Was there a question? No. Okay. Where you're just given one graph, and you want to use this construction of exploding it out into like the sum of its edges. So if we do that and then ask what is the additive product of the edges, the thing you actually get is the universal cover tree of the original graph. Okay, so in this case, you'll get the infinite 3 regular tree. So in some sense, this additive product that we introduced generalizes the notion of taking the universal cover tree of a base graph. Okay. So a couple more examples. The additive product of these 3-4 cycles gives you this graph where, like infinite graph, where each vertex 3-4 cycles are attached. Okay, so this is a way that gives us our infinite graph, which we like to call X. And it's a fact that all these finite additive lifts, G, of your collection of atoms are covered by this infinite graph. Just a tiny asterisk here. This is only true if the finite additive lift is connected, which it will be with high probability. But basically, ignore this asterisk. Good. So now we sort of see a recipe by which we can attack this X-Ramanujan question. If we have some infinite graph X, which is the additive product of some atoms, which gives us a wide variety of interesting looking infinite graphs X, then we can produce plenty of finite graphs G, which are covered by this X, just by taking these additive lifts, these finite additive lifts of the atoms.
So I'm just trying to understand what these X's are. So they're not homogeneous point vertex. They are somewhat whatever you call them, the maps of the infinite thing to itself, which preserve edges, will have finitely many orbits.
Yes, the automorphisms have finitely many orbits. So they're, yeah.
And you don't know which groups. So then you have a group which acts on that, and in terms of group theory, you don't have a description of what your guys are?
I do not. Yeah, so just to repeat what the answer to the question was, in particular these additive products, these infinite graphs, they're quite symmetric in a certain sense. It's not the case that every vertex resembles every other vertex. Sometimes that is the case, right? In this graph, infinite graph, it's vertex transitive. Every vertex is kind of the same as every other vertex. That's vertex transitive. In general, these additive graphs will have the property that, like, there'll be at most, t classes of vertices, where t is the number of vertices in the base graphs, such that every vertex in the same class, resembles each other. So in general, in the infinite graph, there will be, like, in this case, there'll be U-type vertices, V-type vertices, W-type vertices, and X-type vertices. Now, here, this base graph is vertex transitive, so really there's ultimately only one type of vertex. But you can have any arbitrary, 4-vertex graph here, and then in the most general situation, the infinite graph, that's the additive product, will have like 4 different kinds of vertices. Okay. Good. So now we get on to this Ramanujan question, which involves understanding the eigenvalues of these things. So in particular, we're interested in the eigenvalues of additive lifts. This is the finite operation, additive lifts of a bunch of atoms. And similar to the usual case, when you do the additive lifts of a bunch of atoms, you retain the original eigenvalues of the sum of the atoms, and then you get some new eigenvalues. And a cool dream would be if one could show that when you do a random additive lift of a bunch of atoms, A1 through AC, with high probability these new eigenvalues that you get are all bounded by the spectral radius of the infinite graph, this infinite additive product. And if you had that, you would be, it would imply the theorem that we have, that for any additive product, there are infinitely many basically X-Ramanujan graphs. Technically, you have to put quasi here because there might have been some annoying too large eigenvalues in your original sum graph. But either perhaps you can show that that's not the case, or you can just tolerate the fact that your infinitely many graphs might have a couple of too large eigenvalues. Okay, but much like in the Marcus Spielmann-Srivastava papers, we do not achieve that, but we achieve the worst thing, that this holds with non-zero probability, which is just a somewhat silly way to say that for every value r, there exists an r-fold additive lift of your base graphs g, such that the new eigenvalues of this r-fold lift are bounded by the spectral radius of the big infinite graph. Okay, and then in particular, this is kind of like, if you know this stuff real well, this is similar to the situation in MSS 4, interlacing polynomials 4. For every r, every large value of r, you can do an r-fold lift. There exists an r-fold lift that has nicely bounded eigenvalues. And there's this really nice paper by Hall, Puder, and Sawin, which is kind of like interlacing polynomials 5, if you will, where they generalize some of this stuff in the sequence of MSS papers. But for the rest of this talk, I'm not going to talk about showing this for a general value of r, for general r-fold lifts. I'll just, as in MSS 1, talk about additive two-fold lifts. And then once you actually know for two-fold lifts, you can more or less get the desired theorem by just keep doing two lifts, and you'll get larger and larger, the existence of larger and larger graphs, all of which are covered by the infinite additive product, and all of whose second eigenvalues are bounded by the spectral radius. And in fact, given all the previous work, the r-fold case kind of reduces to the two-fold case in the end anyway. Okay. So now we're in a situation where we have some atoms, and we're going to be studying two-fold random lifts of them and trying to understand the eigenvalues of the resulting graphs. Okay, so now a thing that happens is, there's a thing that happens that's also similar to the usual lifting case, which is that you can characterize the new eigenvalues you get when you do an additive two-lift in a slightly simpler way. So the new eigenvalues of the additive two-lift of a bunch of atoms, you always retain the old eigenvalues of the sum graph. The new eigenvalues are the same as the eigenvalues you would get at a random balanced edge signing of the atoms, the sum of such a thing. And just this will become a little bit clearer. Like, imagine what happens when you do a random additive two-lift of some atoms. I'll kind of remind you of the definition. You put a random permutation on each vertex of an atom, which is either the identity permutation on 1 and 2, or it's the transposition. And then you take the quotients to get a permutation, which is, again, either identity or transposition on each edge. And then you make this kind of like just double cover kind of thing where each old edge becomes either just a parallel matching or a crossed matching. And it's very similar to just if you take the edges, and instead of putting identity or transposition and making a little 2-vertex bipartite graph, you just put a sign of plus or minus on each edge. So that's what's going on here. So now I have to annoy you by giving another definition of what is the balanced edge signing of an atom. So what is a balanced edge signing? It's basically you put a random sign, plus or minus 1, on each vertex preliminarily. And then you convert those to edge signs by, again, taking the quotient, or it's the same as product, of the vertices that are the endpoints. Okay? So a balanced edge signing is a way to give, or random balanced edge signing is a way to give an edge sign to each edge in the base graph. But the balancedness property is, again, this property that for every cycle that may exist in these graphs, the product of the signs is going to be positive. It's plus 1. Okay? So it's a special kind of edge signing that's set up so that whenever you go around a cycle, the product of the edge signs is plus 1. Okay? And that's actually where the name balance comes from in the graph theory literature. So this random additive two-lift is, from the point of view of eigenvalues, basically the same as doing the following. You take your atoms, you do a random balanced edge signing of each atom, and then you just, again, literally add the resulting adjacency matrices. And whoops, this will give you a multi-graph, like a graph with integer entries, which is fine. You can think of this as 3 parallel edges, and it's possible that plus 1 cancels with a minus 1, and that edge goes away. That's fine. So yeah, this random two-lift, you can analyze its new eigenvalues by understanding just the normal eigenvalues of the adjacency matrix you get by this operation. Give it a random balanced edge signing to each atom and adding the results. OK, so I'm throwing a lot of stuff at you here, but let's keep going. OK, so let's get to polynomials. That's why we're all here, right? Let's write in a nice way what is the new weighted adjacency matrix when you do this random balanced edge signing plus summing operation. So a nice way to write it is let Q1 through QC be random diagonal matrices where the diagonal entries are random signs. Okay. And now if you conjugate the adjacency matrix A1 by Q1, you can easily check that that exactly gives you a random balanced edge signing of the graph. Okay, so when Q is a random diagonal sign matrix, Q transpose, or whatever, Q, A, Q, gives a random balanced edge signing of A. So that's what we're doing independently for each of the atoms. And then we're just adding the results to get the adjacency matrix of the result. Okay, so actually, if you've seen the finite free convolution stuff, it's quite similar, except instead of random, whatever, unitary matrices, we're conjugating the A's by random diagonal sign matrices. And now we want to understand the eigenvalues of this guy, this matrix. Okay, so just to remind you what we want to show, this is the theorem. This is exactly the theorem we want to show. So you have any atoms, A1 through AC, you do these random diagonal sign matrices, conjugate the atoms by them, add them, get a matrix. You look at its eigenvalues. We want to show that with high probability, or at least non-zero probability, the maximum eigenvalue is bounded by the spectral radius of the infinite graph, this infinite additive product graph. And as I mentioned earlier, we're going to do this without actually knowing what this number is. And just another small comment related to the finite free convolution stuff. This distribution on Q is not unitarily invariant. So like if these were random unitaries, then the result would only depend on the eigenvalues of A but it's not. So like this operation really depends on the whole matrix of A's. Okay, so now we're in a situation which is quite similar to Nima's talk, so glad you're all here for that. So first, we're just going to use some change of terminology. Instead of saying the eigenvalues of this matrix, we'll say roots of the characteristic polynomial of this matrix. And this is bad notation, but I guess the most common notation for characteristic polynomial is phi, so I'll stick with that. Good. And now you're like, hey, interlacing polynomials method. And by virtue of it, we show, it's not too hard to show, that instead it suffices to look at the maximum root of the expected characteristic polynomial of this random matrix. Of course, if you've never seen the interlacing polynomials method before, it like makes no sense that like reasoning about the maximum root of the expected characteristic polynomial would tell you anything about the maximum root of like a non-average polynomial, but you know it does. So yeah, so we have to prove that the interlacing polynomials method applies to this situation, which involves showing that various of these polynomials are real rooted, which they all are. I'll skip that. Actually, it's basically almost an immediate application of a theorem in the Hall-Puter-Sawin paper, which in turn is basically just a reworking of a theorem that's in MSS4. So you know, you apply those things and you find that everything is real rooted and the method applies. One thing actually that Sidon pointed out to me just before this talk, though, is that this is a univariate polynomial. There's a natural multivariate polynomial you could have here, and that guy is not real stable in general. But nevertheless, this polynomial, which is univariate, is real rooted. So you have to use, I guess, the techniques in these papers to show it. Okay, so skipping over that, it now suffices to understand the roots of this expected characteristic polynomial. So let's start by giving this object a name. So we're going to call it the additive characteristic polynomial of this collection of atoms, and I'll call it alpha of these things. So this is a univariate polynomial. I didn't write the variable name. Okay. And as I said, you can show that it's real rooted using basically previous theorems. In fact, we're not going to need that for the rest of the proof. What we're going to show is that the maximum magnitude root of this polynomial is always at most the spectral radius of this infinite graph. But you need the real rootedness to make the interlacing polynomial stuff work. Okay, so we need to start understanding the roots of this expected characteristic polynomial. Just kind of complicated. So let's try to warm up to understand this additive characteristic polynomial a bit. So, okay.
So this is a replacement of the Lead-Hellman theorem?
Yes. This is going to generalize the theorem that the matching polynomial of a graph has its roots bounded in the interval, you know, it's given by the spectral radius of the universal covering tree, which is 2 root d minus 1.
Proof of that theorem?
Well, it's kind of similar to one of Godsell's proofs. But maybe. Okay, let's think of the case when there's only one atom. So you're taking a random balanced edge signing of it, taking the characteristic polynomial, taking the expectation. Well, these Q's are unitary, so actually conjugating a matrix by unitaries doesn't change its roots. So in that case, you just get the characteristic polynomial back. Okay? Now this is an interesting special case too. Imagine you take one graph G and you do this operation of exploding it out into the edge atoms, so writing it as a sum of single edge graphs. Then what is this additive characteristic polynomial? Well, a balanced edge signing of a graph of an edge, a random one, is just a random edge signing. So you get the expected value of the characteristic polynomial of a random edge signing of G. And it's a theorem by Godsell and Gutman that this is the thing called the matching polynomial of the graph, which is usually defined in a combinatorial way. So our additive characteristic polynomial also generalizes the matching polynomial. And let me sketch you a proof of this theorem, because we'll kind of need it in our general scenario. Okay, so the usual definition of the matching polynomial given a graph G and an indeterminate X is it's kind of a generating function for the matchings in partial matchings in the graph stratified by number of vertices involved. So it's a polynomial, the kth coefficient of which is basically up to this -1 sign, the number of matchings in the graph with k vertices. Okay, so why is that also equal to this expected characteristic polynomial of a random edge signing of the adjacency matrix? Well, here's the proof. Taking the expected characteristic polynomial, so we should look at the coefficients of the characteristic polynomial. And there's a totally disgusting formula for the coefficients of the characteristic polynomial of a graph that you can get just by like expanding out the definition of what is a determinant. And what you do is the kth coefficient, you sum over all basically disjoint cycles on the vertex set that have k vertices. And there's some -1 thing going on. And then actually for a general matrix A, you take the product of the edge weights around all of the edges in the cycles. Okay, if these are adjacency matrices of graphs, then this quantity is just 1 or 0 depending on whether or not the cycle is in the graph. So it's some kind of characteristic polynomial it's some kind of generating function for objects which are like vertex disjoint collections of cycles in the graph. So you can get that. And now we're taking the expected value of these coefficients when you randomly edge sign the edges. Now you might think if you have like one cycle, and then you're looking at the product of the entries around that cycle, and then taking an expectation. If you're randomly signing the edges, you would think that expectation would be 0. And therefore, you'd think everything would be 0, and everything would drop out, and you get the 0 polynomial. But that's not quite right because of 2 cycles. So if you have a 2 cycle in the graph, which is just going back and forth on an edge, in a random edge signing, the back and forth on the edge, they get the same sign. So the product of the signs around a 2 cycle is always 1. And therefore, all the terms which are not 2 cycles drop out. And so instead of summing over collections of disjoint any cycles, you sum over collections of disjoint 2 cycles. In other words, you sum over partial matchings. So that was a little fast. You don't have to fully get that whole proof, but I'll say some similar words later, and I wanted to warm you up for it. So this is a sketch of the proof of why the generating function of matchings is the same as this expected characteristic polynomial of a random edge signing of a graph.
By the way, that was the same paper which has got more formula for permanent as a determinant, as co-determinant, the same paper?
I expect not.
Use the Karmakar algorithm. Because it's the same argument.
It could be, I'm not sure. You can check it. Okay, so you can do a similar thing. I mean, now we have to understand this expected characteristic polynomial of this object. And you can do a similar just argument, and you get sort of a formula for the coefficients of this additive characteristic polynomial. And it looks kind of the same. It's basically the kth coefficient counts the number of collections of disjoint cycles with k total vertices, where each cycle has to appear in one of the atoms. Okay, so disjoint colored cycles, as we call them. Okay, so that gives us some kind of formula for the coefficients of this thing, which is good because we're going to be averaging a bunch of these polynomials, and the coefficients of the final average polynomial are the averages of the coefficients. That's nice. Good. And you can see again like how you get the generating function for matchings back here. If you take one graph and explode it out into atoms where each atom is a single edge, and then you look at all the collections of cycles where each cycle comes from one of the atoms, you again get matchings because the only cycles in the atoms are just single edges. Okay, so we have these 3 polynomials, and we have to understand the eigenvalues. And I personally really only know one way of understanding eigenvalues or roots of a characteristic polynomial, which is via the trace method. And the trace method says that if you have a graph G, the kth power sum of the eigenvalues is equal to the number of closed length k walks in G. I guess actually these numbers are the coefficients of like the log derivative of the characteristic polynomial. So it's another little connection to Nima's talk. Now, we all know how to prove this in a very simple way via linear algebra. But what if you wanted to prove this in a horrible way via the only thing I told you about the characteristic polynomial, which is that you can write down this like disgusting formula for its coefficients? You should be able to do that. You should be able to deduce this combinatorial thing about closed length k walks in G from this definition, this horrible definition of the characteristic polynomial. And you can, and it just uses like highly classical generating function stuff, techniques. And the way, somehow it kind of uses like combinatorial interpretation of the Newton relations. And basically, like, all I'll say at a high level is like this is some kind of generating, the coefficients here are some kind of generating function for collections of disjoint directed cycles in G. And this kth power sum of the roots involves like closed walks of length k. And the connection between these two objects is that if you have like a closed walk in a graph, it's kind of like a tree of cycles. What I mean to say is like if you do a closed walk in a graph, you walk around for a while, and then maybe you come back to a vertex you've been before, and that gives you like a simple cycle. And you can kind of like pop it off and then like keep following the walk, and then you maybe hit like another vertex you've been before, and you've completed another cycle, and you can kind of pop it off. And so like a closed walk is somehow composed from collections of cycles. And because of that, and like some generating function stuff, you can go from here to here. Okay. And therefore, you can try to do the same thing for, that was about the characteristic polynomial. And we know a story for the coefficients of the matching polynomial and the additive characteristic polynomial as well. And therefore, we can try to do this generating function stuff to get at the eigenvalues, or the power sums of the eigenvalues of, or just the power sums of the roots of the matching polynomial and the additive characteristic polynomial. So let me repeat this story, but for the matching polynomial. So again, for the matching polynomial, it's kind of some generating function for matchings, disjoint collections of edges. And Godsil in 81 showed that the kth power sum of the roots of the matching polynomial exactly counts the number of closed length k tree-like walks in G, where a tree-like walk in a graph is like one where you're walking, you're only allowed to come back to a vertex by like immediate backtracking. So it kind of looks like depth first search tree kind of things. And why do the roots of the matching polynomial count tree-like walks? Well, if you go to this, it's somehow because a tree-like walk in the same way as before is kind of like what you get if you take edges and connect them in a tree-like fashion. So you can also prove this fact by generating function stuff. Okay, and so now you can do the same story for the additive characteristic polynomial in the same way that the coefficients of this additive characteristic polynomial were kind of generating functions for collections of disjoint cycles where each cycle appears wholly within some atom. If you do this story, you find that the power sum of the roots of the additive characteristic polynomial equals the number of closed length k free-like walks, we invented this goofy term, in the atom set. And I won't exactly say what is a free-like walk, but it's basically a walk in the normal graph, which is the sum of the atoms, which has the property that like when you're doing this thing of walking around and you repeat a vertex and pop off a cycle, that cycle should come wholly from one of the atoms. So it's again kind of like these closed walks that you get by attaching cycles from the atoms together in a tree-like fashion. So this kind of finally made us happy because, okay, now we can attack the roots of this additive characteristic polynomial. We can get some story on them in a combinatorial fashion as like the number of free-like walks that are of a given length k. And indeed, once more, like the tree-like walks in a graph G are exactly the free-like walks that exist when you do this operation of taking a graph and splitting it up as the sum of edge graphs. Because then the only cycles that exist in the atoms are single edges. Okay.
So the point of the randomness is that you get this condition that one cycle has only one color.
Yes, that's right. It kills all the cycles that don't have just one color. Okay. Believe it or not, I'm almost done.
Sorry.
Yeah.
So there is no linear algebraic proof of that fact that you know of?
No, I don't know any linear algebraic proof of this fact. Okay, so as I said, believe it or not, we're almost done because what you can do now, if you care about the largest eigenvalue in the graph, is fix the number of vertices to be a constant and take k to be super duper large. And then the kth power sum of these roots will just be dominated by the largest magnitude root to the power of k. I'll put some 2k in here just in case it's a negative, the root is negative. But anyway, the maximum magnitude root of this additive characteristic polynomial, which is the thing we're trying to show is bounded by the spectral radius of the infinite graph, is that number L such that the number of closed length 2k free-like walks in the atoms is proportional to L to the 2k. So now this kind of gives in some sense a combinatorial interpretation of the maximum magnitude root in this additive characteristic polynomial. And you can always compare this, for example, to the maximum root of the matching polynomial of a graph is that number L such that the number of closed length 2k tree-like walks in the graph is proportional to L to the 2k. Okay, our goal is to show that this is at most the spectral radius of this infinite graph. So how are we going to get the spectral radius of this infinite additive product graph into the picture? Well, again, by the trace method, if you will. So the spectral radius of this infinite graph is also that number R such that the number of closed length 2k walks of any sort, just normal closed 2k walks of any sort in this infinite graph from the worst starting vertex, or in fact any starting vertex, is proportional to R to the 2k. So to show that this is at most this, that L is at most R, it suffices to show that distinct closed free-like walks in the graphs correspond to distinct closed walks in this additive product graph. Or if you want to imagine back to, if you know this stuff a little bit, the matching polynomial, this would be like showing if you have a graph, the number of tree-like walks of a given length in the graph is at most the number of closed walks in the universal cover tree of that same length. And so basically you just need that distinct tree-like or free-like walks in these atoms correspond to distinct closed walks in the additive product graphs. And this is my joke. This is obvious from the definitions, except I didn't tell you the definitions of any of the objects here. But suffice it to say, the whole definition of this additive product graph is such that walks in it kind of look like walks in the sum of the base graphs, but where you're only allowed to come back to a vertex by completing a cycle that's in one of the atoms. So once you process the definitions, it's done, and so you can get this kind of comparison theorem between the roots or the eigenvalues without actually knowing what these numbers are. So this is a picture that may slightly help you, remind you what's going on, and this is where I'll stop. Thank you.
Questions?
Yeah.
Are there some good candidates for uses of expanders with extra structure?
Yeah, I'm glad you asked. Peter, do you want to answer that question? So the question was are there good uses for, it's kind of like constructing optimal spectral expanders, but among graphs that look in a certain way, oh, maybe they're for regular, but they also, every vertex participates in some cycles or some forth. So our original motivation was from the study of constraint satisfaction problems, random constraint satisfaction problems. If you know a little bit about this, if you imagine taking a random regular instance of 3 sats. So you have a random you have like n variables and like a random 3-sat instance on it. So each constraint involves 3 variables. And let's say it's regular, so each vertex participates in the same number of constraints d. You know, a 3-sat constraint, or even better, like a not all equals 3-sat constraint, is kind of like a triangle on the 3 vertices. And so kind of like the graph underlying this random 3-sat instance kind of looks like a random graph that's like the additive product of d triangles. Like, I mean, it's like a bunch of triangles strung together in a random fashion, every point participating in d. And a lot of algorithms associated with random constraint satisfactions are interested in like their eigenvalues. Semi-definite programming relates to this. So we were motivated in previous papers to understand the eigenvalues of random large regular graphs that like are composed from, that don't look like trees, that are composed from like small things like triangles. And that's partly how we got on this subject. And then I think Peter also finished a paper where he's also motivated to look for some quantum reasons for like finite size graphs that locally resemble some infinite graphs, like for example this, we'll cycle back around to this, for example this graph. So finite graphs that resemble this graph locally, there are quotients of it, where you can say that the eigenvalues of this finite graph are similar to the eigenvalues of this infinite graph.
So if you want to keep a gap at the bottom of the spectrum and at the top, for example, then you make a short cycle. That's the way you keep it away at the bottom, and you can optimize on both sides, so you would have a grand generalization of a longer funnel.
Yeah, I mean, one deficiency that this has is like it's the familiar one. It's only controlling the second largest eigenvalue. It would be really great to show, you know, that random additive lifts have spectrum that's like contained in the spectrum, or that resembles the whole spectrum of the infinite graph in terms of on both sides are bounded, and you know, like the infinite biregular tree has a spectrum that looks like the disjoint union of 2 intervals. It'd be cool if, you know, the finite graphs that are lifts of it also had spectra that looked like that. But that's beyond the reach of what we can currently show. Yep.
Is there anything like, are the spectra of these infinite graphs, can you say anything nice about them, or do they have lots of components, or they could be?
Good question. The spectrum of these infinite graphs. So this has been studied before in the case of free products of vertex transitive graphs, which is a case that our additive products also include. And except in extremely simple cases, like this is simple enough, although it took like the PhD thesis of McLaughlin to work it out, you can literally exactly say what the spectrum is. And in general, you can kind of have some like implicit description of the spectrum involving like solutions of systems of equations. And you can kind of make it explicit in the case, not so explicit you can kind of make it explicit in the case where it's like free products of cycles, so things that look like this. But for the most part, you can't really explicitly say what the spectrum look like, except in some pretty simple cases.
But here, it's in a way like the hardest part of Caddison-Singer group is pushed away.
Which part is that?
The upper bound.
Yeah.
It's kind of replaced by something slightly less specific.
Yeah. Well, you could argue that's great. I mean, we don't even have to know what it is. Like, we can still do it. Yeah, no, I understand. Yeah. No, I'm just joking around. Yeah, I mean, it is funny that we bound it without knowing what it is. I mean, you can know it is by other techniques and other techniques that look like this in some cases. There's a really great kind of survey paper by this person called Quinnell, which I can recommend, where he really explains how the best way to get at the spectrum of free products of finite graphs. But yeah, after a while, except in simple cases, you don't have a very explicit description for them.
I think Voiculescu's R transform allows you to compute most of these that have been computed.
Yeah, it's this Quinnell stuff. I mean,
I was asking you whether you have new groups. Maybe you've done something new there as well.
No, I haven't done anything new, at least. Maybe Siddhant is working on it.
So free product with amalgamation.
Yeah, I would like to get a good description of it, actually.
Amalgamated over some simple.
Yeah, so in some sense, the Voiculescu methods are the same methods that one can use to implicitly compute this spectrum, but the final result is not like a number. It's like, oh, it involves like, okay, the roots of like a system of polynomial equations.
We like this.
Yeah,
It's algebraic.
yes. I mean, yeah, in some sense it is explicit. It's not like super explicit, but it's pretty good. Okay, thanks a lot.